All right, so on problem 13, these are also exponential functions, but notice that there is only one term taken to an exponent. So here we're going to use our definition of log. We're going to take the log of both sides. So where we're going to start is we're going to turn this into b to the x is equal to some number, and then take the log of both sides. Then the power property will allow us to bring the x out of the exponent. Okay, so for 13, problem A, I have 2.5 e to the negative 1.2x is equal to 1. Okay. This is the part that I need to get isolated at, just the base to the exponent. So I'm going to divide both sides by 2.5. So that gives me e to the negative 1.2x is equal to, and 1 over 2.5 is equal to 0.4, I think. Okay, it is. All right, so now I've got the form that I wanted, so I'm going to take the log of both sides. You can take either base 10 or base e. Since there's an e here, I would go ahead and use natural log. So I have the natural log of e to the negative 1.2x is equal to the natural log of 0.4. All right, well now the reason I use natural log is because from here, I either by the property or I can move this around front. Log base e of e to the x is x. So this just becomes negative 1.2x is equal to the natural log of 0.4. To get x by itself, I divide by 1.2, and I get x is equal to the natural log of 0.4. Whoops, I added too many zeros in there. Divided by negative 1.2. This is your exact answer. So to find the approximation, you just plug this in your calculator. And again, to save time, the answer is 0.7636. Okay, for B, we have 0.05 times 1.15 to the x is equal to 5. Again, this is what I want by itself. So I'm going to have to divide by 0.05. And let's see. 5 divided by 0.05 gives me 100. So 1.15 to the x is equal to 100. So you can do, I'm going to use the log on both sides. So I have the log of 1.15 to the x equals the log of 100. Oh, well, that turned out handy because 100 is a power of 10. I can move this around front, so this tells me that x times the log of 1.15 is equal to 2. So to get the x by itself, I divide by log of 1.15. Now if you don't see that, that's okay, because you can just plug in the log of 100 divided by the log of 1.15. So x equals 2 over log 1.15, again, is your exact, and the approximate is 32.9501. And again, you want to take it to 4 decimal places. Okay, for C, you have 11 plus 5 to the 3x is equal to 20. All right, I want this by itself. So I'm going to subtract 11 from both sides. So 5 to the 3x is equal to 9. I don't care which one we use. I think, what did I use? Oh, I used log base 10. So log of 5 to the 3x is equal to the log of 9. The whole point of doing that was so I can bring this around. 3x times log 5 is equal to log 9. So to get the x by itself, this is all multiplication, so I'm going to divide by 3 times the log of 5. So I get rid of that, and my exact answer is the log of 9 divided by 3 log 5, and the approximation is 0.4551. Okay. All right, so if we want to solve log equations, again, there are a couple ways to do this. If we have log base b of x equals log base b of y, that implies that x equals y. If the logs and the bases are the same, then the arguments have to be the same for them to be equal. Okay, again, it just kind of makes sense. All right. So if you have a log equals a log, you just set the arguments equal to each other. So I have the log of x minus 1 is equal to the log of 3 minus x. The bases are the same, so that tells me that x minus 1 has to equal 3 minus x. When I do that, that gives me 2x is equal to 4. So x is equal to 2. Okay. Now the deal on this is, remember, your argument has to be greater than 0. It cannot equal 0. It cannot equal a negative number. So I have to check and see if putting 2 into either of these makes the argument less than 0. So if I'm going to check x plus 1 or minus 1, 2 minus 1 is 1. If I check 3 minus x, this becomes 3 minus 2, which is also 1, so everything is fine. And that is a solution. Okay, for part B, I have the natural log of x squared is equal to the natural log of 4. Bases are the same, so I set the arguments equal. So I have x squared is equal to 4. Now, this is a quadratic, since I would use the square root property. So that tells me that x is equal to positive or negative 2. But I want to check them. Okay, so let's see. I'm going to check x squared. Well, for negative 2, negative 2 squared is 4, so that's okay. If I check 2, 2 squared is 4, so they check. So both of these are solutions. Okay, so if I have log base 3 of 2x minus 7 is equal to the log base 3 of 5x. Bases are the same, so the arguments have to be equal. So 2x minus 7 is equal to 5x. That tells me that 3x is equal to negative 7. So x is equal to negative 7 thirds. Okay, so let's check. Alright, so let's check 2x minus 7. Excuse me. So 2 times negative 7 thirds minus 7 gives me negative 14 thirds minus 7, which is less than 0. Excuse me. So there is no solution. This is extraneous. Okay. So for 15, notice you have logs all over the place. Okay, and you need to turn this. So you're going to take these and turn them into log base b of x equals log base b of y. we know how to combine these if you're adding two logarithms or if you're subtracting two logarithms. So that's how we're going to do that. Excuse me. Okay, so for a, if I have log of x plus log of 2x plus 5 is equal to the log of 7, I can combine these two and I get the log of x times 2x plus 5 is equal to the log of 7. So now I can combine these into this argument equals this. So I have x times 2x plus 5 is equal to 7. 2x squared plus 5x is equal to 7. Again, this is a quadratic, so I have to set it equal to 0. 2x squared plus 5x minus 7 is equal to 0. Let's see how this factors. I know this has to be a 2x and an x. Plus 7 minus 1. Okay, so this tells me that x is negative 7/2 or x is 1. Okay, so now I have to check them. Okay, so let's check negative 7/2. Okay, well, the log of x is the log of negative 7/2, which is undefined, so that is extraneous. So let's check 1. So log of 1 is equal to 0, so it's okay. The log of 2 times 1 plus 5 is the log of 7, which is okay. And the log of 7 is okay. So this one works. Okay, for 15b, have the natural log of x plus the natural log of 3x minus 1 is equal to the natural log of 10. Okay, same basic process here. I'm going to turn this side into the natural log of x times 3x minus 1 equals the natural log of 10. Now, same base, so the arguments have to be equal since the expressions are equal. X times 3x minus 1 equals 10. 3x squared minus x is 10. Quadratic, so I set it equal to 0. 3x squared minus x minus 10 is 0. So this is 3x and this is x. So let's see, this is plus minus 2 and plus 5. Okay, so my x is negative 5/3 or 2. So I want to check both of them. So let's check negative 5/3. Okay, well, my first term is the log of x, so the natural log of negative 5/3 is undefined, so that is an extraneous solution. Okay, so let's check 2. So the natural log of 2 is okay. The natural log of 3 times 2 minus 1 is the natural log of 5, which is okay. And then the natural log of 10, so 2 is a solution. Okay, so now I have the log base 5 of 2x minus the log base 5 of x minus 1 is equal to the log base 5 of 4. Okay, well, We're not going to multiply this time, we're going to divide because it's a log minus a log. So this becomes log base 5 of 2x divided by x minus 1 is equal to the log base 5 of 4. Okay, that's fine. All right, bases are the same, so the arguments have to be equal. So 2x over x minus 1 is equal to 4. So I'm going to multiply both sides by the least common denominator. That cancels out. I get 2x is equal to, and let's go ahead and distribute, 4x minus 4. So that gives me negative 2x is equal to negative 4, so x is equal to 2. So let's do our check. So the log base 5 of 2 times 2 is okay. Log base 5 of 2 minus 1, this is positive, so that's okay, and that one's okay, so this is a solution. Okay. All right, so on 16, here we have a little bit different situation. We only have one logarithm equals a number. And what you're going to do here is you're going to use the definition of logarithm. If I have log base b of x equals y, that is equivalent to saying b to the y is equal to x. So by taking the using the definition of log, that means I can get this out of the argument. So A, I have log base 2 of x squared plus 7 is equal to 3. So my definition of log tells me that 2 to the third is equal to x squared plus 7. So this tells me that 8 is equal to x squared plus 7. You can subtract the 8 and factor it, or you can just subtract 7. So I have 1 is equal to x squared. When I take the square root of both sides, I get x is equal to positive and negative 1. So let's check. If I check 1, log base 2 of 1 squared plus 7 is log base 2 of 8, which checks. Let's check negative 1. So log base 2 of negative 1 squared plus 7 is also positive, so that checks. So both of these are solutions. So here on B I have the log of x squared minus 3x is equal to 1. Okay, I have to remember that if it's not explicitly written, here the base is 10. So using the definition of log, I can rewrite this as 10 to the first is equal to x squared minus 3x. 10 to the first is just 10. I'm going to subtract it. So 0 is x squared minus 3x minus 10. This factors into x minus 5, x plus 2. So x is 5, x is negative 2. Okay, so let's check both of these. All right, so let's check x equals 5. So the log of 5 squared minus 3 times 5, that's 25 minus 10, which is positive. I'm sorry, 25 minus 15, which is 10, so that works. Let's check x equals negative 2. The log of negative 2 squared minus 3 times negative 2 gives me 4 plus 6, which is 10. So they both check. Don't automatically discount a negative. Okay, and we have log base 5 of 4x minus 7 is equal to 2. Again, there's only one logarithm, so the only way to get this out of the argument is using the definition of log. So this means 5 to the second is equal to 4x minus 7. So 25 is 4x minus 7. Add 7, I get 4x equals 32. So x is 8. So now I'm going to check. Excuse me. So log base 5 of 4 times 8 minus 7 is 32 minus 25. So that checks. Okay, we've got a couple more problems, and we will do that in the next video.